Hello, it's me, Steve. On September 22nd, 2017, I made some measurements of the sun's path throughout the sky, uh, and I did a solar noon test, which is the same as zenith, for Sly Sparkane because he requested that we do it, and I actually already have posted that video as is unedited. I'll link it below. But the equinoxes are both pretty awesome because at solar noon on the equinox, you can get your exact latitude just by measuring some angles of a solar noon. You can also use a clinometer, which will give you a direct reading, but I did it with a what's called a gnomon, which I'll refer to from now on as an instrument, and the shadow that was cast. And I measured both the instrument and the shadow. But anyway, just some quick background here. This is not to scale, obviously. It says it right there, see. Um, it is shot along the ecliptic, which is the path the Earth takes around the Sun in its orbit. And what I wanted to illustrate here with this is the Earth's inclination, or the Earth's tilt, to the ecliptic. But just quick note, the average distance from the Sun to the Earth is defined as one astronomical unit, and it's in kilometers there for you. But the Earth's orbit is eccentric. It's not a perfect circle. It has an eccentricity of about 0.0167, which means at its closest, it's 147 million kilometers, and at its furthest, it's roughly 152 million kilometers. Obviously, there's 100s in there, but that's so the Earth is not at the same distance from the Sun all the time. And why am I getting into this? I'll show you in a second here. This also is not to scale. All right, this is as if you're looking 90 degrees down upon the ecliptic, um, on our solar system towards Earth's North Pole. All right. So, like I said, it's not to scale. I had to greatly exaggerate the size of the Earth compared to the Sun. I had to greatly shrink the distance and greatly increase the eccentricity so you could see what I'm trying to illustrate here. Okay? Um, the separation's far, 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 far greater than this. Um, but there's people seem to be a little confused about which way north points from the actual axis of Earth's rotation. Well, it always points towards Polaris at the present moment in time, without getting into how that, with Earth wobble and all that stuff. But Polaris is about 433.8 light years away. That's 27,433,979 astronomical units. Remember, I showed you what an astronomical unit was before. At those distances, kilometers, miles aren't even useful. And down there, I put how many astronomical units are in a light year. So that angle is so small to our vantage point. It looks like it's Polaris is always due north. All right. Now that wouldn't happen if something else as Earth orbits the sun didn't happen. And as you can see here, I have a white arrow along Earth's orbit showing the direction of that the Earth orbits the sun, and I have a little curved arrow showing the rotational direction of Earth. I'm not including the moon on here because it's not relevant for anything or what I'm going to show you here. All right. So if you look, I have a purple dot with an N. That's compensating for the inclination at 23.5 degrees, which I showed you in a previous slide. All right. And as you look, that purple dot always faces the same direction in space. That means it tracks itself with its orbit around the sun. The purple dot does not move. You see here where the N is labeled for north, but you move along to one of the equinoxes and you see it still faces the same direction. It's not at 90 degrees to where it was at the one with the N on it. All right. This is actually pretty important because that's the reason why we get the seasons. If it didn't do that, we would always have either the northern or southern hemisphere always facing the sun, and we wouldn't have any seasons or very little variation in seasons. All right. So just to show you here, this is the relative position at winter solstice, spring equinox, summer solstice, and fall equinox. And as you can see here, the reason why I made the eccentricity so exaggerated here for Earth's orbit around the sun is to sit here and illustrate to you that even though the Earth is physically closer to the sun during winter in the northern hemisphere, that seems kind of counterintuitive. And during the summer solstice, we're further away from the sun physically, but in the northern hemisphere we experience summer, and this is due to the Earth's 23.5-degree tilt. In the winter, we're tilted further away we're tilted away from the sun, and in the summer, we're tilted towards it in the northern hemisphere. So, in the summer we get more direct sun rays than we would during the winter. At the equinoxes, though, something interesting happens, which I'm going to get it here in a second when I get into the experiment. And here I just showed, this is just to show the nighttime side of the Earth in the darker blues, just to show you how that is in relationship to everything else. All right, the fall equinox. Obviously, this is from Google Earth. This is just to show you, if you're looking perpendicular to the sun's rays as they hit the Earth at sunrise, the red X was my location on September 22nd. As the sun was rising at my location, and here I have the tilt of the Earth included. All right, so you can see that during the equinoxes, the tilt we don't receive. It's not a significant part of the equation here that I'm going to show you, because at perpendicular to the sun's rays, it can be modeled just as the tilt isn't significant because it's 90 degrees relative to the sun rays. As you can see the point that says north. All right, so you go 90 degrees to where the solar rays are, and the tilt is not a significant factor during the equinoxes. All right, so here's as if you're looking, if you cut the Earth in half, and you're looking at the Earth from the sun's point of view during the fall equinox. All right, the ecliptic's the white line, the north and south poles are labeled, and the black dashed line is just to show you the perpendicular to the ecliptic and our tilt in degrees from the ecliptic. And I was at about 41.5 degrees latitude. All right, and this just shows you the sun's rays hitting the Earth. Now the sun's rays hit the Earth basically, the sun's rays are parallel to one another. The sun is huge. It's a non-point light source. All right, so that's what I was trying to illustrate here. Obviously, I can't show you the sun's rays with an arrow tip going directly into me at 90 degrees, but you get the picture here. All right, so this is as if we're looking at it from the sun, and we cut the Earth in half. All right. Okay, so now that we know that, we know that the tilt of the Earth isn't a significant factor here, although I still have the purple dot where actual North Pole would be during the fall equinox. We can set up an experiment to get our latitude, our actual physical latitude on the planet. All right, and here's the gnomon and the surface put not to scale, because it isn't to scale. Now, when I ran the experiment, the table I was using was only a few feet wide, okay? And you see the surface, I extended it as a plane. Why did I do that? Because the Earth's circumference is 24,900 miles, all right? So something that's 3 feet in diameter isn't going to show significant curvature. It's not going to show any curvature, so you can treat it as a plane. And where I have the surface, that's what you're looking directly at the plane. You're looking parallel to the plane, all right, of the Earth's surface. That's why I extended it. Even the Earth's curvature doesn't really come into significance at the human scale until about 11 kilometers anyway, which is about 6 or 7 miles, probably closer to 7. That's why when we make geologic maps, we like to use a 7.5 minute quadrangle, or which is a 1 to 24,000 scale map, because we don't, when we draw cross sections, when we do it the whole length of the map, we don't have to take the curvature into account. After that, it starts to show itself. Um, but when you're dealing with something that's several feet wide compared to the entire Earth, you can just model it as a plane. So basically, how the experiment went, and you can actually physically see it in the video that I linked below, is I have my surface, I set up my instrument, and my instrument at 90 degrees to the surface. And that gives me 90 degrees to my latitude, as you can see here. All right. And I drew, 41.5 degrees north on there. So this is a greatly exaggerated model of my experiment on the Earth. Obviously, my experiment wasn't extending out into space, okay? It's just to show you so you can see it. And here you can see the direction of the solar rays coming in, all right? So what we get with that is we get a right triangle, all right? Since the instrument is parallel to the 41.5 degrees from the center of the Earth, I don't need to do anything with the 41.5 degrees from the center of the Earth. I can just use my instrument. And if we do that, I know what my latitude is, but I can make some predictions to see if the experiment I run actually worked. All right. So as you can see, it's really tiny here. You have an angle A and B. The angle A is closer to the Earth. The angle B is further away. And my instrument at solar noon, which is the same thing as the zenith, will cast a shadow. And it's the blue line here with the two dots at either end, and it's labeled shadow. So we can get a length. So my angle A, all I have to do is subtract my latitude from 90 degrees, because I'm dealing with only one hemisphere, and I get 48.5 degrees, should be the measurement for my angle A. My angle B, I subtract that 48.5 degrees from 90, and I get 41.5 degrees, which is my latitude. All right, so that's what if my experiments run correctly, and it's perfectly, everything's exact, those are the numbers I should get, and I would get my latitude as a result. All right. Well, when I actually ran the experiment, my instrument height was 10.55 inches. My shadow was 9.20 inches. Okay. And the reason why I did that, and my instrument was only 1/10 of an inch in diameter. And the reason why I did that is because 1/10 of an inch is a good solid metal rod that's not going to be subject to the whims of the wind as easily. And the reason why it was 10.55 inches is because between 9 and 12 inches is a good length for a gnomon in order to do this accurately. Anything less than 9 inches, your margin of errors are going to be greater. Anything greater than 12 inches, the shadow's going to cast a significant penumbra, which I've also done videos about on shadows, and you won't be able to get as accurate reading on your shadows. So it's a good middle ground for that. All right. So I take my triangle, and basically here I blew it up and tilted it 90 degrees so you could see it better here. So I have 10.55 inches on one of my legs, 9.20 on the other. So I can use the Pythagorean theorem to get my hypotenuse, which you can see I did here. I'm not going to beat into it for you, but there's the math. All right, and why do I need the hypotenuse? Well, in order to get these angles, I need that. All right, so what I'm going to do is I'm going to calculate my angle B first. All right, and it's not a difficult calculation. I need the sine of B, which is equal to the opposite divided by the hypotenuse. The opposite leg, obviously, is the 9.20, and the hypotenuse we have is 14. And I get roughly 0.65714. Now I have to get B isolated by itself, so I have to do a little algebraic manipulation here, and I actually have to take the inverse sine of that 0.65714. And I get my angle B as 41.08212 degrees, which is roughly 41.1 degrees. Now, calculating angle angle A is so much easier at this point because, as you know, a right triangle has to equal, all the angles have to equal 180 degrees. We already know the 90, we know the 41.1, so we just subtract that from 90 to get angle A, and we get 48.9 degrees. All right, so we have our triangle now. All right, and what does that tell us? Well, what that tells us is that our angle B is our latitude. At the equinox, at solar noon, that works. That direct number is your latitude. All right. Now, obviously, I was off a bit. All right. I was off. Here's the calculation of the margin of error. I was off 0.4%. Not a big deal. I was actually pretty accurate when I did this. So I went to Google Earth and I did as straight a line due south as I could to see how far that would put me from where I actually was. The green star is where I am. The red line with the ball at the end is due south. And my margin of error is roughly 51.78 kilometers or 32.17 miles. So it's not a big margin of error on a planet with a circumference of 24,900 miles. All right. So the experiment worked pretty well. I took some readings throughout the day that day, which I'm going to save for another video. But I just wanted to show you how that works on the Equinox. And I don't usually plug like websites and stuff, but sunearthtools.com is a good website. As you can see here, if you want to know where solar noon is in the sun's path for a day at your latitude and longitude, you can go to this website and it does all the calculations for you. And it's pretty sweet. Here you see the red arrow pointing down. That's how you determine solar noon. Obviously, the yellowish brown numbers are the times during the day. And it actually will compensate for daylight savings time. And I'll show a little video at the very end of this of how I used this. And it gives you charts if you print out a PDF with some basic information on it that you can use to determine things. It'll even give you the sun's elevation in the sky in degrees. And just so you know, time zones. If you notice in the upper left-hand corner here, it says GMT -6. That's Central Time in the Western Hemisphere. Every time zone west of Greenwich, England, is -1, -2, -3, -4, -5, etc., etc. And to the right would be just 1, 2, 3, 4, or to the east would just be 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. So that's what that -6 means. It just tells me Central Time. So if you see that, because you need to plug that in to get the information. If you don't know that Central Time is -6, you can be like, what? But I mean, you can just Google it and it'll bring it to you. But it means Eastern is -5. And that means Mountain Time is to the west of Central. Yeah, that means that's -7. All right. So it does, and in here it gives you extra information. And here I'm giving you some extra information. They actually are very friendly when it comes to suggestions and stuff, and you can see that here. So I think that's pretty much it. I just wanted to show you how I ran that experiment and how I calculated my results and stuff. And like I said, if you want to see the actual field work with no editing for my solar noon measurement, it is linked below. But anyway, that's it, and I hope you learned something. Since today is the autumn equinox, I'm just going to show this website real quick, which calculates solar noon, your zenith, the path of the sun in the sky from your location, and basically just shows you, puts it on Google Earth. That's really close to where I am. Everything's compensated for here. We are still in daylight savings time. I'm time zone -6, which would be Central Time, and there's the date. And if we look here, that's really close to where I am. We can see that gives solar noon at 12:40. The other website gave it at 12:41. So it's close. And as you can see, since we have 12 hours a day and night, solar noon is essentially equivalent to the zenith. All right, but here's a more detailed calculation. It's sunearthtools.com. That's the website. And here you go for that information. And there you can still see date and time.